Traffic control signals are power-operated devices that direct traffic alternately at intersections. They assign the right-of-way to each intersecting street in an efficient manner. In this program, we will describe basically how engineers determine if a signal is needed, how signal controller phasing works, and how signal timing works. Traffic signals are the most restrictive of traditional traffic control devices. They should only be used when nothing else will do. The first step in determining the need for a signal is to conduct a study of the intersection. There are several types of common studies. A traffic volume study counts vehicles and pedestrians. Specially designed solid-state traffic counters can count vehicles going both directions on a street, one direction, or even one lane, such as the turning lane. The count may be all day or at particular times of the day. A spot speed study provides speed distribution information. After measuring individual vehicle speeds, sample means and standard deviations will indicate overall traffic flow efficiency. A physical condition diagram provides engineers with a detailed scale drawing of the area. It includes street and curb dimensions. An accident analysis provides accident histories and collision diagrams. This analysis can provide before and after studies and evaluation of requests for signals. Gap studies require in-person observation and data gathering. By measuring the unused space in a traffic stream, engineers can help determine how much space is potentially usable by cross-street traffic. Delay studies also require on-site work. They evaluate stopped time performance of vehicles and pedestrians. This measure is applied in determining the need for traffic signals. The next step is to apply the results of studies to a series of warrants. If one or more of 11 warrants are met, it is usually justification for a signal. Let's look at the warrants. Minimum vehicular volume means the volume of intersecting traffic at the intersection is the principal reason a signal is necessary. Interruption of continuous traffic means the traffic on a major street is so heavy that a minor street suffers excessive delay or hazard in entering or crossing the major street. A combination of warrants means that although no one warrant is satisfied, the previous two are each 80% satisfied. Minimum pedestrian volume means that a signal is warranted if a certain number of pedestrians per day during certain periods need to cross a street or intersection. The school crossing warrant involves the frequency and duration of gaps in traffic and the number of school children needing to cross at an intersection. A traffic engineering study is needed to make this determination. Progressive movement means a signal is needed to help maintain proper grouping of vehicles and regulate the group's speed. Accident experience refers to the number of accidents at an intersection, as well as the use of previously unsatisfactory remedies. A systems warrant is intended to encourage concentration and organization of traffic flow networks. It normally applies to the intersection of two major routes. 4-hour volumes means that traffic volumes on both the major and minor streets are observed at sustained levels for a minimum period of 4 hours during each day. Peak hour delay means that heavy traffic conditions on a major street result in undue delays to side street traffic during the peak hour each day. And finally, peak hour traffic volumes on major and side streets comprise a warranting condition. Conditions at an intersection may satisfy a warrant. But what about off hours at night or during light traffic? What about a signal malfunction? The answer is flashing operation. A flashing signal, yellow one direction and red the other, at a 4- or 3-legged intersection is commonly used for these situations. And as an interim measure prior to removing an unwarranted signal or at new signal installations just prior to full signal turn-on. A flashing signal reduces stops and needless delays to both Main Street and side street traffic. By keeping traffic moving, it reduces fuel consumption, and it reduces the signal's use of electricity by 50 to 65%. At flashing intersections, minor street drivers should have an unrestricted view of the main street, and the traffic volume must be low. After the flashing lights are installed, accident patterns should be monitored carefully. If there is an increase, the lights should be changed. If conditions change at an intersection, a signal should be removed. Changes could include increased delays, decrease in traffic on either approach, increased accidents, increased fuel consumption, or air pollution. Once study results satisfy signal warrants, a signal may be installed. At all intersections, a display will have a minimum of 2 faces to ensure safe operation in the event of bulb failure. Basically, a signal system consists of the lights, which can be configured in a variety of displays, pavement detection loops, and the control mechanism or controller box. There are 2 basic types of traffic control signals. Pre-timed signals work with a clock-like mechanism. They repeat a sequence of signals over and over, regardless of whether or not there are vehicles or pedestrians present. Actuated signals change their timing depending on the movements of vehicles and pedestrians. There are 2 types of actuated signals. Full actuated signals, which are controlled entirely by the movements of vehicles and pedestrians using them, and semi-actuated signals. They are first part of a system of many signals. Secondly, they act as a response to the movements of vehicles and pedestrians in their immediate area. Now let's look at controller phasing. A complete in-depth discussion of phasing would be too lengthy for this program. Instead, we will look at 3 intersection situations and show how signals would be phased for each one. The most common intersection is the 4-legged intersection. For this situation, the controller operates in 2 phases. One phase allows the traffic on one street to go. Then, the second phase allows the traffic on the crossing street to go. At the end of the phase, there is a clearance interval, which is the time the yellow light is displayed and traffic clears the intersection. If an additional street or streets are added, we have another situation. For each additional leg, the controller normally operates in an additional phase. Things get a bit more complicated in our 3rd situation, one that allows for left turns. This situation usually involves a special left turn lane and requires left turn phases, but at the expense of green light time for through traffic. There are two common strategies for providing left turns. One method is called the protected left turn. In this movement, a left turn arrow allows left turners to go, while a red light stops the opposing through traffic. It helps the left turner, but slows the through traffic. It adds phases, one for the left turn, a phase for through traffic one way, a phase for the other left turn, and a phase for the through traffic going the other way. The other strategy is called the protected permitted left turn. This movement involves what's called a split phase for the left turn only lane. The left turners first have a circular green light permitting them to turn while there is through traffic. Then they have a left turn arrow protecting their turn. This method allows left turning but provides more green time for through traffic. A protected left turn preceding a through movement is called a lead left. A lead left has a couple of advantages. First, drivers tend to react quickly to lead left, so more vehicles tend to get through the intersection. Second, it works well where separate left turn only lanes do not exist. The disadvantage to lead left is that left-turning vehicles may continue to turn even after opposing traffic gets a green light. When the left turn phasing follows the through movement, it is called a lag left. The lag left also has two advantages. First, both directions of through traffic can start at the same time, and it approximates the normal driving behavior of motorists. Its disadvantage is that left-turn vehicles facing a yellow indication may be trapped in the middle of the intersection. The decision to have left-turn phasing is generally based on through and turning traffic volume, traffic delay, and accident rates. Another aspect of signal control is timing. When the controller regulates timing, it is determining how long each movement or phase will last. There are two ways controllers handle timing. An older-fashioned controller uses an electromechanical system to specify times for each phase. As a camshaft turns, electric contacts close to activate a light, the green one way and the red the other. Newer solid-state controllers use microprocessor technology. They have a computer memory that remembers phases and timing. The memory is altered through a keyboard just like a desktop computer. The controller can be adjusted manually or activated by sensors in the pavement or elsewhere, or pedestrian push buttons. These state-of-the-art devices can also be controlled remotely from central control centers. The center may have sophisticated computers linking networks of signals. Some cities control virtually all of their traffic signals from one point. Sophisticated centers use specialized software called Transit 7F, which optimizes traffic flow. Many centers also have closed-circuit television equipment at critical points on highways to assist them in solving traffic congestion and safety problems. In this program, we have described how engineers determine if a traffic control signal is needed at an intersection, how signal controller phasing works, and how signal timing works. The first step in determining the need for a signal is to conduct a study of the intersection. There are several types of common studies, including traffic volumes, approach travel speed, and accident history. The next step is to apply the results of studies to a series of warrants. If one or more of 11 warrants are met, it is usually justification for a signal. Warrants include minimum vehicular volume, minimum pedestrian volume, delay, accident experience, and a combination of warrants. On off hours at night or during light traffic situations, signals may be set to flash. Flashing signals improve traffic flow and they save fuel and electricity. Once study results satisfy signal warrants, a signal may be installed. Basically, a signal system consists of the lights, pavement detection loops, and the control mechanism or controller box. Controller phasing involves the portion of a signal cycle allotted to specific traffic movement. At a common four-legged intersection, the controller operates in two phases. One phase allows the traffic on one street to go, and the other allows the traffic on the crossing street to go. To create a protected left turn, the controller operates with a split phase. Left turns can be lead left if the protected left turn precedes the through movement, or lag left if the left turn phasing follows the through movement. Another aspect of signal control is timing. When the controller regulates timing, it is determining how long each movement or phase will last. An older-fashioned controller uses an electromechanical system of dials and cams. They are set manually to specific times for each phase. Newer solid-state controllers use microprocessor technology. They have a computer memory that remembers phases and timing. The memory is altered through a keyboard, just like a desktop computer. These state-of-the-art devices can also be controlled remotely from central control centers. The center may have sophisticated computers linking networks of signals. Some cities control virtually all of their traffic signals from one point. For more information on these devices, check the manual on uniform traffic control devices or other similar documents. For more information on other IRF videotapes, call the International Road Federation at the numbers on your screen.